Good morning, everyone. I'm Allison Okamura. I'm your session chair for this session on mechanisms and actuators and force and tactile sensing. I'm really pleased to introduce our keynote speaker, who is Antonio Bicchi. He is a professor of robotics at the University of Pisa, is a world-renowned researcher in mechanics, dynamic systems, control, and haptics, and we're very pleased to have him tell us about natural machine motion and embodied intelligence.
Thank you very much, Alison, for the introduction, and thanks to the organizers for inviting me here. I think I can move here. Yeah. No. A short line. Okay, so talk is about natural machine motion and embodied intelligence. Natural motion is something that we all expect from our machines, from our robots, to achieve at some point. I don't believe, if I think of a robot in the future, I don't believe it will move like the stereotype robot motion or like the industrial robots that we had in the past. I'd rather think that they will like more like humans do. And you can see here some of the feats that a human can do. Deepest drive, 44 meters, 54 meters. And you can jump from standing almost as high as you are. You're tall. These are probably far to be reached, but robots and humans compare very poorly. Robots compare to humans very poorly. This is a slide I borrowed from Alinor Buschaffer, who has led a project on actuation and natural motion of robots for some years with us. The difference is the body. Another topic of the talk is human hands and robot hands. Robot hands we have seen robot hands of different types, some very beautiful hands, some are being made now, some go back in the past, and some of these were really exceptional engineering features. So, for instance, JPL Stanford hand at MIT AI in 1989 was already capable of measuring the friction coefficients of objects by sliding a finger with a sensor, detecting object by texture, controlling with reflex grasping, or follow and reconstruct shape. This was back in 1989. So why this kind of hand, or the other beautiful hands that we have had, didn't make it to the real world? You don't see them in industry, you don't see them in real application, you don't see them in service. What is the reason? Part of the reason is that machine motion is not good enough. At that time, we had a motor box that was much larger than the hand itself, Bowden cables that would break very often, unfortunately. But even today, recently we have made this hand that's rapid prototyping, more modern design. You can do nice things. You can handle different objects. You can also manipulate a little bit, like a syringe or a Dremel. But things that are untold very often is that still the motor box is large, the tendons are fragile, and the programming of this hand takes a long time. Now, programming might not be a big problem. If you are very good at programming, computational power is very cheap now. If you compare yesterday Pumas, for those of you that are old enough to remember, in a Puma we had 160 kiloflops back in the 80s. But today, the dumbest smartphone has 40,000 times the same computational power. So machine intelligence has gone a long way from there. But if you look at machine motion instead, in the 60s, the Puma had servo motors. And in 2010, most robots have servo motors. We didn't make much advancements. I think it's time to move forward. 2020, maybe we will have something different, maybe muscles for robots. The body makes a big difference, and intelligence is related to the body. I don't believe in intelligence per se. I believe in robotics. The intelligence has to be embodied, at least in part, and I will argue on this. Embodied intelligence, if you ask a philosopher, It's the theory of having cognition that depends on the kind of experiences that come from having a body. And it concerns the fact that the very structure of reason itself comes from the details of our embodiment. But concerning the hand, for instance, there are claims that the modern human brain came after the hominid hand. That meaning that the hand shaped the way we think and we do things. This actually goes much farther back in the past, 6th century before Christ, and Anaxagoras thought that man was the most intelligent of animals because he had hands. What is embodied intelligence in a more precise sense? This is my definition. There are plenty of definitions, so I just said, why not one more? Property of a physical system, the body, to adapt and interact with its environment to naturally produce the desired function. And I underscore body, environment, natural motion. So body plus environment make a function. I'll come back to this later on. How far are we from implementing any of this natural motion? There are some good news. We have been stuck for a long time with servo motors. I think there are some good news. Labs are changing quickly. These are pictures from my own lab a few years ago. And these are new things that happened in the last few years. So it's much more colorful, for one thing. And the reason is that you have new technology. Additive manufacturing is important. There are many different brands and things that you have there. But also new embedded microcontrollers, the Arduino style. New sensors, magnetic sensors, Kinect. All those things we dreamed of some time ago. Hardware in the loop tools, new operating systems, software, middleware, toolboxes, ROS, YARP. Those things are making the cycle of innovation so much faster than we were used to. So things happen in the lab at a different time scale than we were used. Not only enabling technologies, there are also some enabling science results that are changing the landscape. For instance, understanding how humans move is something that helps us a lot. Everybody knows that the human body, each joint is actuated by at least 2 muscles, and there is a wealth of results on how humans skillfully control the impedance of their limbs through both control of the posture and the co-contraction of the muscles. And there is another result from science that I think is very important to us. There are synergies. So many functions of the human body require coordination of a large number of muscles. So in emitting a single phoneme, ba or pi, I'm using something like 40 muscles in my body, going from the mouth to the tongue, to the pharynx, to the diaphragm. And all of them are coordinated to do ba instead of pi in a different way. So you may wonder, how can people speak and know what they're saying at the same time? Maybe not everybody, but there is scientific evidence for the existence of sensory-motor synergies. All of those muscles move together because they are considered as a one unit by the central nervous system. So you don't have to think of this co-activation. For hands, Santello and Flanders and Sutting in 1998 analyzed the statistics of a large database of human grasps. And they came up with this idea of postural synergy. This is very simple. You look at the covariance matrix of how the joint move in a human hand in everyday task, and you take the principal component. You call the first principal vector first synergy, and so on and so forth. If you use the first synergy and second synergy and third synergy together, you build a subspace. And if you move in this subspace, you already explain 90% of the covariance of everyday grasp. If you only use 84%, the first one is already 50% of the covariance. It's a lot. So the problem is how to make robots that are soft yet strong, simple but also dexterous, intelligent, and practical. And our approach is mixing soft robotics technologies and theory of human synergies. So from models, from the original models, we have been moving forward the scene, not just us. I mean, there is a whole number of people doing this. Series elastic actuators introduced in the 90s, more recently variable stiffness actuators, where you have motors that can not only change their position, but also their motion, their stiffness. So for instance, in a completely similar way as to what you have in the human joints, you can control the reference and the co-activation. Motor control, people call those reference and co-activation signals R and C, and they use lambda from Feldman theories to define this. But you have, in this motor here, you can use exactly the same thing. So you can control the servo motor with exactly the same inputs. And you can choose the springs, and this is the device that we have developed in the lab. You can choose the springs so that the characteristics are very similar to those of the human muscles. That's why we call them robot muscles. We have been seeing many devices. We have been designing many devices. And it is still important to go forward and build new actuators. But it's also time to move forward, in my opinion. And I believe that naturally moving machines might have more applications than we imagine. And so we started with this idea of crowdsourcing the exploitation of the technology, making the technology readily available, creating a community, sharing fully the design, fully open hardware and software, make it simple to program, modular hardware and software, low cost, make everybody able to use variable stiffness actuators or muscles to build their own robots. So that's why we started this natural machine motion initiative to foster the diffusion of soft actuation for robots that move like we move. And here is the website that we have started. You can put there your own drawings of your own device, schematics, instructions, actuators, accessories, or you can download and print out that cube that I showed before if you like, and use it in your lab. Those cubes can be used as building blocks for doing a snake or an hexapod or a humanoid that has the possibility of controlling the stiffness while it moves, co-contracting just like the human do. But let's go back to hands. Okay, so the first synergy alone explains 50% of the covariance. So we say, why don't we start from there? If you move a hand according to the first synergy alone, then you have a single degree of freedom, basically. It's a subspace where you coordinate motion. That is not enough. The idea of synergies is not enough to grasp an object, because if you close your hand, either you're not grabbing the object, or if you do, you get inside. That's not the point. So putting together soft technologies and synergies, you can explain perhaps how you can control the hand. So the idea is that you have this reference position, that is the mesh hand, and the real hand. You can control the reference R on this manifold of the synergies, and then the stiffness. So the force is generated via the error between the real hand and the reference hand times the stiffness that you control. So this sounds like a nice idea. Can we implement? From theory to practice, there is need for some more radical changes in the design. So we started implementing a new hand that substitutes joints with roll-articular pairs and has ligaments that are elastic. So each finger can be deformed, can be almost torn apart, and goes back in position. So it can withstand impacts. This is the Pisa-IIT SoftHand that we put together. And here are very first experiments with that. So the hand moves and can comply with different objects. So you can observe that the shape of the hand is different depending on the object itself. The hand has 18 anthropomorphic joints, one soft synergy, one motor. Here is the hand grasping different objects. And here is grasping handles. The hand can can be mistreated, even severely. You can slam it on a very rigid environment. Now, how do we use this kind of hand? We thought that it was interesting to learn from humans how to use a robot hand. So we made a little interface for a human to use the hand. And it turns out that humans can use the hand in a very natural way, as you can see from here. Possibly it's the fact that the hand is so anthropomorphic, not only in the way it looks, but also in the way it moves, according to this first synergy, that makes it befit the body schema of the person. And kids can do wonders. We were very surprised by this, and we learned a lot, because kids were able to do things that we never thought the hand could do, like picking a coin from a table. And they were using deformations of the hand. Purposefully, they would deform the hand to do the task. So we started using this idea, and then we went further. You can use the hand as if your own. Recall that the hand has 1 degree of freedom, 1 motor, but has the 18 joints. And you can deform the hand on purpose for doing tasks. So, for instance, you can push the hand against the environment to shape it. You can grab a ream of paper. And then, the same is, you can also softly take one sheet of paper out of the same ream. The hand can be used, it's very sturdy, can be used in a workshop. So you have several operations here. You can use the drill, you can turn the handle, you can use the machine. You can even push a button, as you see on the left bottom line. Pushing a button was not originally planned in the design of the hand. But you can do that. The hand is pretty strong, so you can also use the fire extinguisher, which is 10 kilograms heavy. The hand can also be delicate. So if we control both the reference and the stiffness, we can do things like handling strawberries or noodles like this. And finally, you can get some dexterity by exploiting the environment constraints. So this is the key message, I think. If you exploit environmental constraints, you can do things with hands that you probably didn't think of before. So question is, can we program a robot to use a soft, simple robot hand as effectively as humans do? Using simple, soft hands changes the grasp planning deeply, I think. So thinking of where to place your fingertips for maximizing force closure measurements, for instance, might be less important. And I tell you, I've been working years on these problems. But if you look at the classical literature pictures, what strikes me is that in all those, there is no hand, while hands are central. And the physics of them is important. Thinking of how to approach the environment to shape the hand properly for a grasp is more relevant. And reasoning about robot-environment interaction is key to me. So here is one example of what I mean. This is a very simple example. So you are grabbing the mug with the same hand, the same object, the mug, and the same on-off control, right? But once you are taking it from the top, and once you are making from the side. Yeah? So it's 2 different grasps, and you can see that the hand does 2 different things depending on the affordance. Right? So the control is the same. The control is open or close, as simple as that. The hand has 2 different shapes. So programming time, 0. Well, I shouldn't say so. Programming time is what it takes to you to know where to put the hand at the very beginning. So this is what I call body environment that give you a function. This is what I call embodied intelligence. Let me close with an application I'm very interested these days. It's the SoftHand. This is in collaboration with some hospitals in Italy and also in the United States. The hand is very simple and probably robust and low cost as to be useful. And here you can see the first experiments with amputees that are using the hand. This is very preliminary results, so the hand is still to be optimized, but you can see that they very quickly learned how to use this hand, and they're very happy. Here are a few more. You can use the hand as if it were your own. It moves like your own, and you can do things like managing tissues or a group of cups. Here is the hand opening turning a key and opening a door. There's a lot of work to do, but we believe that this will impact somehow the possibility of giving hands to people at a reasonable cost that are robust and can be useful and have an impact on the real life. So these are the people that have done most of the work, and these are the sponsors, and thank you for your attention.
Good morning, ladies and gentlemen. I'm Le Wei Tang, and I come from Tsinghua University in China. I would like to present our paper entitled Dynamic Trajectory Planning of Planar 2 Degrees of Freedom Redundantly Actuated Cable Suspended Parallel Robots. This work was done in collaboration with the Robotics Laboratory at Laval University in Canada. The main contribution of this paper is to show the dynamic capability of cable suspended robots using redundant actuators, especially for the trajectories that extend beyond the static workspace. In this paper, we study a mechanism in which 4 cables are attached at a common point mass and effector, whose motions can be controlled in the plane. Since there are 2 degrees of freedom and that 4 actuators are used, the robot is redundantly actuated. To discuss the dynamic trajectories, the working plane is divided into 7 regions. It is shown that the end effect cannot reach region 1 because of the direction of gravity. It is also noteworthy that the region 3 is referred to as the first closure workspace, where arbitrary accelerations can be theoretically generated. The antipodal theorem is used to simplify the tension constraints. For instance, considering the configurations in the left figure, cable 2 and cable 3 form a sector containing cable 1 and cable 4. If the cables at the boundary of sector are in tension, then the cables inside will be in tension as well automatically. So 4 cable constraints can be simplified to only 2. In the next 2 slides, with 2 horizontal straight line trajectories are studied to obtain the characteristics of such cable robot. The first trajectory is a horizontal oscillation going through the first closure workspace. Based on antipodal theory and interval arithmetics, the global constraint is obtained and shown on the graph. The second trajectory is located below the lines through point 3 and point 4. An alternative mechanism is adopted to overcome the interference using only 2 cables with 2 pins below. We can observe that the feasible frequency region has 2 asymptotes pertaining to arbitrary amplitude in serial. Compared to previous research, we can conclude that redundant actuators can greatly enhance the capability of dynamic trajectory planning for cable suspended robot. If you come to see my paper, I can show you some videos of experimental validation. Thank you.
Hello everyone, my name is Hamid Khakpour, and today I'm going to present you the work I have done with my supervisor, Dr. Lionel Briglen, from Polytechnique de Montreal, and it's about augmentation of the workspace of a special cable robot with 3 degrees of freedom using differential system. As everybody knows, cables, they just can pull the objects but not push them. So in a cable robot, to fully constrain the moving platform with n degrees of freedom, at least n plus 1 cables are required. Also, it's shown in the literature that if more cables are used in the structure of cable robot with a proper design, larger workspace can be expected. However, using more cables would result in, of course, using more actuators, which itself result in higher cost of the robot and more complexity of the controlling procedure of the mechanism. So we have proposed to use differential systems in the structure of cable robots to improve their workspaces while the number of actuators are kept at minimum. In these 2 figures, you can see 2 cable systems. In the left figure, the 2 cables are individually actuated using 2 actuators, and so they can produce 2 constraining forces. While in the right figure, the 2 cables are connected to the same actuators through a differential system, and so they just can produce 1 constraining force. And so we have shown that there are some differences between their performance with respect to the one which are fully driven, and this is more discussed in the paper. And these cables, they have some particular properties which are helpful in the design of the cable robots. In this work, we have mainly focused on the spatial cable robots, and we have shown that cable mechanisms, and we have shown that these mechanisms are working similar to a single cable system in which its attachment point to the base platform is moving on a plan. And then we have used this cable differentials in the structure of two cable mechanisms. In the left, you can see a cable suspended robot, and in the right figure, you can see the fully driven, fully restrained cable robot. And then we have calculated their workspaces, the range closure and range feasible workspaces, and compared them to those of fully driven cable robots with similar structures and the same number of actuators. And we have shown that using these systems, we can have better and larger workspaces. I would like to talk more about this work in the interactive session, and I would be happy to see you there. Thank you very much.
Hi, I'm Shohei Shirafuji, and I'm a PhD student in Osaka University. The title of my paper is Tendon Routing Resolving Inverse Kinematics for Variable Stiffness Joint. The variable joint stiffness is one of the important functions of the human musculoskeletal system to accomplish various tasks adaptively. One of the typical methods to realize the variable joint stiffness is the method using tendon-driven mechanism and nonlinear elastic components. In this method, the joint stiffness is adjusted by pulling several nonlinearly elastic components, preventing movements of the joint, as shown in this figure. We have two control motors to adjust joint positions and stiffnesses, considering the complex relation between the joint positions and the joint stiffnesses carefully. The control of them will be simplified if there is any mechanism to separate the control of joint positions and stiffnesses mechanically. In other words, complex calculation is not needed if we can control the joint positions and stiffnesses by separate motors independently. In our paper, we propose the methodology to construct such mechanism, and we call this mechanism as tendon routing resolving inverse kinematics. In short, we call it as toric. This is one example of toric for a manipulator with 1 degree of freedom and non-linearly moment arms. Toric is composed of step pulleys and moving pulleys. We can adjust joint positions and stiffnesses of this manipulator by driving separate two motors through the proposed mechanism. It makes easier to change the joint stiffness while the manipulator is moving. We can construct such mechanism for various tendon-driven mechanisms. Thus, in the interactive session, we will introduce the detail of the methodology to design toric for a given tendon-driven manipulators, including a manipulator with multi degrees of freedom. Thank you.
Hello everyone, I'm Yong-Tae Kim and I'd like to talk about our research drum stroke variation using variable stiffness actuators. The motivation of our research is implementing variable drum stroke using variable stiffness actuators. In drumming applications, stiff actuator has possibility to break the drum membrane, and also series elastic actuators has limitations on variety because it has static stiffness. However, variable stiffness actuator has both safety and variety. So what is the various stroke? There are two kinds of strokes in drum stroke field. The single stroke is making one sound with a one swing, and double stroke makes two sounds with a one swing. So we implemented drum rolling using double strokes. So for the drum rolling, we model the physical relation between the drumstick and drum membrane, and we also found the proper stiffness for the drum rolling as the blue boxes. In double stroke, the core variable is the stiffness. The responses are varied by the stiffness variation. In high stiffness, there is no bounces and there are only single strokes are appear. And if the stiffness is a little bit decreased, bounces are appeared and the double strokes are start. And there are also some region that allows the drum rolling. It means the first stroke and the bounces this stroke are come out after the stroke, so it makes the sustainable strokes. If the stiffness are a little bit more decreased, there are no bounces and there are only single strokes are appear. So let's see our video. This video shows the stiffness variation and the response are changed by the stiffness variation. So there are some regions that allow the stiffness. Sorry for sound, and this is the rolling region. Yeah. Thank you for watching, and I'd like to talk about more details about our research, and I want to show more fun videos about drumming in the interactive session. Thank you.
Hello and welcome to my presentation on compliant robotic systems on graphs. I'm Stefan Groothuis, I'm from the University of Twente, and this is work that I did together with my supervisors Stefano Stramigioli and Raffaella Carloni. So the importance of safe human-robot interaction increases, and this can be achieved by using variable stiffness actuated joints. At the same time, the design space of compliant systems increases because of these new types of actuators and their placement, for instance, along manipulators, which will give you new articulation types like uni-articulation and bi-articulation. Graph theory allows, we propose graph theory as a modular approach, modular modeling approach, where VSA is a building block for multi-degree of freedom systems, and where the graph defines the interconnection. So here we have a model of a variable stiffness actuator and the proposed graph on the right. So the three vertices there are the stator mass, the rotor mass, and the load mass. And they are connected by the edges there, and there, which are associated by the input force generated in the motor, the tunable spring, and a possible disturbance force on the load. So this is then the building block for more complex systems like this one, where there are multiple types of articulation, so uni-articulation, bi-articulation, and tri-articulation. In the same way as with this actuator, the graph can be built, which then looks like this. Actually, in a very straightforward way, you can get the dynamics equations. Now we can optimize this system, the design of this system. So suppose that I impose a task on this load, like this back and forward motion. And I let an optimal controller choose the optimal stiffnesses for the 7 actuators that drive these 4 loads. Then what we can see is that for 2 actuators, indeed the stiffness is changed along during the performance of the task. For the rest of the actuators, they are actually kept constant. So it's not necessary to put an expensive and heavy and difficult variable stiffness actuator in these locations. So these and these are this and this. So this actually then leads to design guidelines for complex compliance systems. So if you want to know more, the details come by at my kiosk this afternoon. Thanks very much.
Hello, my name is Nico Mansfeld and I'm a PhD student at the German Aerospace Center. Today I'd like to show you some recent work on the control of elastic joint robots I have been doing together with my advisor Sami Haddadi. Intrinsic joint elasticity has been becoming increasingly popular mainly due to three reasons. The first is impact robustness, the second is energy efficiency, and the third is performance increase. And this work contributes to the third capability. In particular, we consider two problems. The first is which states can an elastic joint with limited dynamics reach from equilibrium? And the second is how can an elastic joint robot be stopped as fast as possible? First, we use a simple 1 degree of freedom elastic joint model where the motor velocity and the elastic deflection are bounded. For the first problem of reaching desired states, we find the reachable set in the phase plane and derive the time optimal trajectories. We also analyze the influence of all joint parameters on the maximum velocity. For the second problem of breaking to equilibrium, we take the same approach and also find the breakable set in the phase plane and the according trajectories. Having found the reachable and the breakable set, we combine these in order to analyze the overall joint performance. And we find parameters for good energy storage and release capabilities. Finally, we extend our methods to n degree of freedom breaking of elastic robots by using a decoupling approach. Now I'd like to show you a video that illustrates the performance of the controller. We use a KUKA lightweight arm and emulate joint elasticity by joint impedance control. So first the robot is undamped and it shows strong oscillations. And after activating the controller, the robot stops quite quickly and afterwards shows is very strongly damped. If you'd like to know how it works, please meet me at the interactive session. Thank you.
Hi everybody, my name is Matteo Lasagni, and I'm here today to present you a shape-shifting display based on force guiding particle chains. A shape-shifting display is a screen made of tiny robotic particles which is able to take on a form of a target 3D model. Each particle is indeed able to interact with the other particles and rearrange themselves into a different shape. If you want to make high-quality display, so displays with high resolution, we need to combine together tiny particles and in a large number. But here we come into scalability problems, because if you have many particles which have to stick to each other and which are able to change their connection dynamically, we need to build in each particle strong actuators and latches. But in general, the strength of an actuator grows with its size. And because of that, we run into a problem, as the particle also would have a constraint on the minimum size. To overcome this problem, we devised this system in which multiple chains are arranged regularly one beside the other to form a foldable surface. And each chain that you can see here can fold and outline a corresponding slice in the target 3D model. To simplify particles design, instead of having a strong actuator here within the particle, we concentrate the actuation outside the chain, like here, in a way that a single external actuator exerts a compressing force on the chain and therefore on each particle by means of these two tendons. And each particle embodies a very simple and weak actuators inside that slightly deform the particle in order to exploit the external force and fold the chain. This is why we called our approach force guiding particle. Okay, in this way, we have been able to build a shape-shifting display that can show arbitrary shapes. Having a single external actuator let us to build a system with an arbitrary number of particles, because if you have a larger number of particles, we simply increase the strength and then the size of the actuator. The simple design of each particle let us to make particles that are very tiny, and in this way, we have a system that is scalable and flexible. Thank you very much.
Good morning. My name is Jakub Lengiewicz. I will present the joint work of my team on one of important features of programmable matter, which is the ability to perform mechanical tasks. Programmable matter is a concept of future metamaterial that can autonomously assume any desired shape or perform some other mechanical tasks. For example, can lift load. Currently, the most advanced approaches to the realization of this technology come from the field of modular robotics. However, the number of problems have been encountered, mainly issues of miniaturization of modules and cooperations of many tiny modules to do some desired task. We base our analysis on the concept of spherical modules proposed by the Claytronics teams from Carnegie Mellon University. The Claytronics design seems suitable to be miniaturized, and as it doesn't possess any moving parts. The basic actuation mechanism is controlling of electric fields beneath the surface so as to move two modules around each other. The strength of such an actuation is relatively high, but it is still too low to carry the collective weight of the modules in moderately large structures. This is because the overall strength of such structures is quite low. Our idea is to equip the modules with secondary connection type, the strong connections. Strong connections can make it possible to build durable and rigid frames, which are then moved in opposite directions by propelling modules, producing the overall force. So we call this actuator microstructures because of the microstructure of this. So we have developed several types of actuator microstructures and several variants of each of them. The linear actuator seems to be the most promising, but there are some others, so-called pump actuators and the rotor actuator. So they have some particular advantages as well. We have analyzed the proposed actuators both analytically and numerically using a properly adapted discrete element system. The results prove that the overall force scales with the volume of the structure. For example, in one of the analyzed cases, the actuator can lift the 8 times as much as it weighs itself. I will be pleased to discuss the topic in more detail during the interactive session. Thank you for your attention.
Hi, I'm Christopher Parrott, and today I'm going to be talking about the work I've been doing with my colleagues at the University of Sheffield on a high-speed genderless connection mechanism for self-reconfigurable modular robots called HiGen. So for those unfamiliar, the purpose of connectors in modular robotics is to allow for separate robotic entities to be joined so that they can be moved together, share power and communicate. Such mechanisms can be categorized based on one of 3 methods of connection, be it gendered, where there's 2 distinct types, commonly known as active and passive, bigendered, where there is a single type with gendered elements, and genderless, where there are no gendered elements. We have developed this high-speed genderless connection mechanism that, to our knowledge, is an order of magnitude faster than existing genderless approaches. Because of its genderless design, it allows either side to disconnect in the event of failure. Other features of it include self-separation and electrical pathways. The connection between 2 HiGen units is achieved using a hook-to-hook design. Hooks follow a helical path in and out of the mechanism, latching underneath the opposing connector's hooks. An outer shroud translates with these hooks to maintain rotational alignment. Because of this hook arrangement, either set of hooks can freely detach without action from the other. And when both sets are retracted, clearance is produced, aiding self-reconfiguration in large modular configurations. To verify the connector design, 2 units were produced and 3 main experiments conducted. We were able to verify the high-speed claim by measuring the actuation and connection time to be under 0.3 seconds. 200 trials were conducted to verify, to test the unit's ability to handle misalignment, and we were able to test that the unit can handle a vertical load of at least 2 kilograms. Single-sided disconnect was also verified as part of this testing when resetting the experiments between each of the misalignment trials. Thank you, and I look forward to talking about this more in the interactive session where I have a few samples with me.
Okay. Hello, my name is Jörg German. I'm from EPFL in Switzerland, and I have a paper named Stretchable Electroadhesion for Soft Robots. So recently, there's been a great interest in the development of novel soft robots, such as the octopus arm from IIT that we see here. And soft robots have many great potentials. But in certain situations, soft robots may need connection mechanisms that are controllable, highly deformable, soft and stretchable. And this is what we focus on here, so enabling controllable adhesion for soft robots, and more specifically, developing stretchable electroadhesion. So the way electroadhesion works is that flexible electrodes with a specific pattern are embedded into a polymer, and by applying a high voltage to the electrodes and approaching a surface, adhesion forces are set up between the pad and a substrate. And here in this work, we wanted to investigate how the adhesion forces develop when electroadhesive pad can undergo large mechanical strains. So we came up with a simple fabrication process for stretchable electroadhesive pads, and we fabricated samples with different electrode geometries, and in order to assess the performance of the pads, also an experimental setup to characterize the normal and shear attachment forces under different strains. And one of the striking results of our experiments is that the normal forces decrease with stretching the electroadhesive pads, whereas the shear forces actually increase with a higher stretch of the pads. And we believe that this is due to an interplay of mechanical and electrical effects that happen when stretching the pads. Now I'd like to show you a little video that shows this work. So here you can see the soft and stretchable electroadhesive pads. And for our experiments, we have this stretcher, so we can stretch the pads in two axes. And so here comes an example that shows that the shear force under low strain is actually lower than if the pad is higher stretched, such as we can see it here. And another advantage of the higher stretch is actually that the surface area is increased, which means the shear force can be further increased by having a greater surface area. Now, another example of what we did is we strapped it over a finger, and we show something that a human being could not do with just one finger. And also just to show the holding, the potentials of that force, it's holding here up a robot. So I'd be happy to talk more about this with you.
Hello, everyone. My name is Rachid Bicchi from École Technologie Supérieure in Montreal. Today, I'm going to present you our work on new design method for multi-axis force sensors. There is three important questions. The first one is why multi-axis force sensors are important. Over the last years, there has been strong desire to bring robots in the human environment. And the force sensing capability is one of the key features to help for better interaction and safe interaction. So the second question is how to spread their use. Of course, a good sensitivity, better accuracy, lower noise, a good compactness, and a lower cost will lead to a better integration of this kind of sensors in different applications. The last question is how to improve their performance. We think and we believe that the geometry of the mechanical structure combined to a proper displacement sensing technology are both important to enhance the sensor performance. So to prove that, we tried to design a miniature 3-axial force sensor. And first, to improve the shape of the mechanical structure, we used this symbolic mathematical model, which link the applied wrench applied on the structure to the pre-selected displacement on the compliant structure. And this model allows us to easily define the design constraint and choose the best shape for the mechanical structure. Also, we used a capacitive sensing system, which contained 4 cells, and by doping the dielectric between the 2 conductive plates, we was capable to improve the resolution and the sensitivity of the sensor. So as a result, we obtained this prototype, which is 3-axial force sensor. It was easy to fabricate. Also, it's very sensitive, and it respects all the application design constraints. I will be happy to present you a prototype in the interactive session, and I will respond to other questions for more details. Thank you.
Hi, I would like to present the work of my PhD student, Atașescu Kitarian. He has done the work at my group in University of Munich. We developed a framework to create arbitrary perceptual modes from a given set of physical sensors. You may know sensory substitution from human domain. Lost sensing modality is often replaced by processing a different domain. For example, a blind person can get acoustic signals telling something about the structure of the surrounding world. And we would like to move it to robotic domain, where a typical service robot needs to sense a variety of sensor signals, which requires a large number of physical sensors. We would like to reduce the number just by applying the framework to create additional modes. These virtual modes result in different processing chains. So there is a second task on our approach to find the best configuration for this specific setup of frame rate, sensitivity, and measuring range. What we're trying to combine is a set of physical sensors on the robot on the left side with modalities we want to develop on the right. And we provide a transformation graph. This graph can be built based on the back of transformations. These transformations actually are based on physical laws like Hooke's law, stretching of a surface to force, and something like this. The graph actually contains transformation blocks, and we distinguish different types of transformation blocks, some combining just 2 values, 2 signals, some doing iterative combinations like gradients or more complex structures. Each of the blocks has some complexity value attached to it and some description of the error propagation, which allows us to build an optimal graph. And you see that for a specific combination of a physical sensor at start and a goal sensor we want to develop, we can have different chains. And the optimality tries to find the best solution in the graph to apply the sensor. We tested it on several applications. Here, for example, an accelerometer. You can use an IMU to measure accelerations, but for slow velocities, for slow accelerations, the signal-to-noise ratio may be bad, so it may be better to use a camera to use accelerations at slower rates. And here is the system developed by our framework. A second example is, for example, a touch sensor, which is consisting of a membrane with dots on it, and the camera measures actually the deflection of the points, telling you the force distribution and the force magnitude from observation. This sensor gives you additional possibility not to measure the force, not only to measure the force, but also to distinguish what type of contact you have, if it's a hard surface or if it's a soft or deformable surface. I would like to discuss the details in the active session. Thank you.
Hello, everyone. My name is Selman Sakar. I'm presenting on behalf of my colleagues from ETH Zurich and University of Zurich, our new microrobotic platform for characterization of plant cells. Our main objective in this project is to measure both the mechanical and physical properties of pollen tubes while they are growing. And if we have a reliable method to be able to characterize these properties, then we want to move on to look for key factors that play a role in biomechanics, which proteins, which ionic flows, etc. And then using the estimated parameters, we can develop computational models for predictive power. So the main requirements are we have to be fast because the workspace is relatively big. It's millimeter scale, but the cells are small. They are microscale. And we want to characterize many cells while they are growing to get high throughput. And we also need to track the cells while they are growing because we want to make the measurements exactly at the same location at the tip or at the stalk. And we want to integrate the whole system with confocal microscopes so that we can do fluorescent microscopy. This is the system. It's called real-time cellular force microscope. And the force resolution is around 5 nanonewtons, while the positional accuracy is 10 nanometers. And we can work in a large workspace. There are 4 main modules in the system. I'll go through them quickly. First of all, we have a positioning system. Two positioners are connected to each other. One is coarse, the other one is fine. And we can benefit from both for speed and also for high resolution. And the second module is the force sensing part. We are using capacitive MEMS force sensors. They are commercially available. FemtoTools is a spin-off from our lab. And then the third module is the acquisition and control part. We are using real-time computers and FPGA. And the fourth is the computer vision automation. So using this system, we could be able to measure stiffness at different locations during cell growth, and we could be able to generate the stiffness and topography maps while they are growing. And for one measurement, it takes around 1.5 seconds, so it's quite fast. And lastly, we generated these strains with fluorescent calcium so that we can measure these fluxes and this is real time. So while the cell is growing, we mechanically stimulate and look at calcium, how it changes, and move on. So we can make the measurement at exactly the same location relative to the tip so that we can make comparisons afterwards. And yeah, thank you very much. If you want to know more about the details, please visit me during the interactive sessions.
Hello everyone, my name is Prangular. I'm a PhD student at KTH, and today I will present you our work which is about content classification. In household environments, interacting with different kinds of contents in containers is an important task because wrong manipulation can cause some hazardous results like spilling. So in order to prevent this kind of failures, we train our robot to classify the content in the containers by grasping them and then collecting visual and tactile data. So our motivation comes from human sensory modalities, vision and touch. According to the researchers, there is a division of labor between our senses. For instance, while vision observes the haptic environment, touch collects information about the surface texture. So in our work, we use a visual Kinect device to collect the visual data, and the Shunkant to collect the tactile data, and these tactile readings are used to complement the missing area under the finger in the visual data. So this is our data set, and as you see, there are different patterns for each content types. So this tells us that we can, by learning these patterns, we can learn the contents in the containers. So in our analysis, we use k-means to see if there are natural clusters in our data set. And we use other learning methodologies like KNN, QDA, SVM to learn the relations between tactile visual data and content types. So according to our results, most of the time single sensor modality is enough. But in some cases, combining vision and tactile increases the accuracy rate. So this is the end of my presentation. Thank you for listening, and if you are interested, you can come to the interactive session.
Good day, everyone. My name is Emmanuel Dean. I'm working in the Institute for Cognitive Systems at the Technical University of Munich. Today I'm going to talk about this paper named 3D Spatial Self-Organization of Modular Artificial Skin. This is a joint work with Philip Mittendorfer and Gordon Cheng. Skin is as important for robots as it is for humans. It can potentially extend the set of capabilities of a robot. For example, it can allow the robot to interact with the world with its own whole body. It can extend the social skills of the robot. It can be used for classification of objects or events. So in general, the skin can be used to change the way the robot interacts with the environment. One of the problems of artificial skin is the way it's calibrated. Usually this is done manually, and in this paper we present a novel methodology for self-calibration of this kind of sensory systems. In our case, we are using our cellular skin, which is a tactile multimodal sensor which contains 4 different modalities. It can measure forces, it can measure inertial data, temperature, and proximity. The methodology is composed of different stages that goes from cellular to cellular calibration. This includes self-network discovering of the cellular array. It also contains patch calibration, which includes 3D reconstruction of the whole patch with respect to a local frame, and also multiple batch calibration using external sensors. In this case, we use a camera as an external sensor. The methodology has been tested in different scenarios. For example, this one, which is a single patch calibration in normal conditions, but also large patch calibration considering occlusion. We also have tested our system in multiple patch calibration with a large number of cells. For example, the one we use in our robot, which a single patch can contain hundreds of cells. The results obtained from this calibration process can be directly used for designing controls to change the dynamic behavior of robots. In this case, we can show that we have non-compliant robots and we can make it compliant. We can also use the modalities of the sensor to create a collision avoidance system in the robot. If you are interested in this topic, please come to the interactive session. Thank you.
Hi, I'm John Wabet. Today I'm going to talk about research of my team at Stanford University. Minimally invasive medical interventions brought a lot of benefit for the patients, such as short recovery time and small scar after surgery and so on. However, the doctors lose their benefit from touch sensation because they're no longer allowed to put their hands inside a body like open surgery in the past. To overcome this lack of touch sensation, we designed a force-sensing needle and 1-degree freedom haptic feedback system, which can read and deliver the interaction forces between the tool tip and the tissue. Especially, we are going to talk about how force-sensing location makes difference in membrane puncture detection, which is very simple but most common task during the needle intervention. First challenge of reading interaction forces was minimizing the effect from friction force along the needle. To minimize the friction force, we wanted to put the sensor at the tip. However, the most of commercial force sensors are too big to implement it. So we use FEG sensor, which reflect the specific wavelength depending on the strain of optical fiber. We also added the small features at the needle tip to increase the axial sensitivity of this force sensing needle. Interesting thing was observed when it compared the force at the tip and the force at the base. We tapped the plastic block with this tool several times. As you can see from here, the reading from both locations looks very similar. However, when you insert this tool into the phantom, which has 3 membranes inside, it shows different results. Because of the friction, you could see the direct force effect from the data at the base. To explore more of this, we built 1-degree freedom haptic feedback system. The user holds this haptic display and push the needle into the phantom. Total 10 healthy users were asked to stop when they feel membrane puncture from the haptic display. The haptic feedback mode was selected randomly, and from this user test, we could see the haptic feedback based on tip force sensing give higher success rate in membrane detections. In conclusion, tip force sensing resulted in higher membrane detection rate than feedback based on other sensors. We recently designed multi-dot haptic display, and we plan to test it with physicians in the future. Thank you for listening, and please come by our interactive session booth for more details.
So good morning. I am Alessandro Serio from Centro Piaggio and IIT. I am not the author of the paper, but I'm presenting the work of Carlos Rosales. Well, our setup consists basically in a robotic fingertip and a probe, and we want to use this robotic fingertip and a tactile sensor in order to gain information about the shape of the object of the probe and its friction coefficient. Well, for doing this, we use the intrinsic tactile sensor. The intrinsic tactile sensor is composed by a force torque sensor and a fingertip. And from this sensor, we can measure contact point and force at contact. Then we have a QK arm, and we have a RGBD sensor for the point cloud of the scene. The shape and the friction coefficient over the surface of the object are approximated by a Gaussian process. The implicit function of the representing the shape is exploited for the exploratory strategy. We use a Cartesian impedance controller. Here, KC is the impedance, the Cartesian impedance. XD is related to the trajectory, while FD is the desired force in order to keep in contact the fingertip and the object. Well, in these two experiments, so the top, in the top you can see the contact force. So this force is useful for detecting the contact, non-contact state, while in the bottom graph you can see the estimation of the friction coefficient ABS cardboard during the contact state, during the contact. Here we show the box model. The smaller points are the example point from the point cloud. The bigger points are the sample over the model. And the color gives an idea of the friction coefficient value. Black means -1, and green means a value between 0 and the estimated value. So, thank you.
Hello, everyone. I'm Ray Lee from MIT. I'm going to talk about localization and manipulation of small parts using gel-side tactile sensing. This is joint work between MIT and Northeastern University. Robotic insertion of small parts can be challenging due to small tolerances typically involved. We have developed a tactile sensor for in-hand localization and demonstrated its capability for small parts manipulation with the USB insertion task. The gel-side fingertip sensor provides high-resolution 3D geometry of grasped parts. It consists of an elastomer gel coated with a reflective membrane, LEDs of multiple colors, and a camera that captures the deformation of the gel. The sensor itself is compact and can be mounted on a robot gripper. Its resolution can be as high as a few microns, much higher than what is otherwise available. These are the 3D geometries of different objects obtained from our sensor, where the brightness represents the protrusion of the object surface. On the left is the 3D image of a human hair, where you can see one hair on top of the other. In the middle image is my fingerprint, and on right is numbers on a $100 note. The sensor can give tactile information in real time. We use the sensor to demonstrate USB insertion that requires sub-millimeter accuracy. We hang the USB cable freely in the air and mount gel-side sensor on backside gripper. The robot then grasps the USB connector, estimates its pulse, and inserts it into the socket on the table. To do the insertion, we first create a 3D tactile map of the USB connector by registering gel-side images of the USB connector. Next, the robot localizes the USB pulses in its gripper by using feature matching method. With inverse kinematics, the Baxter robot can do the USB insertion with high accuracy. This is a video showing one of the insertion experiments. Out of the 36 insertion experiments with different USB pulses, 34 were successful. If you want to know more about our work, please come to the interactive session. Thank you.
Hi, I'm Carlo Ciliberto, and I'm going to give you an overview of a work we performed in collaboration across different departments at IIT, the Italian Institute of Technology in Genoa. So the far end goal of the work was legged locomotion on the ICAB robot that you can see here on the right, and legged locomotion on rough terrains. So on rough terrains, the main assumption that we would like to have, the fact that the contact surface between the robot feet and the terrain is a flat surface. Well, this assumption does not hold anymore. So usually solutions can be mechanical, where we try to regulate the properties of the leg, both active or passive, or try to improve the sensor acquisitions, the perception of the environment through the interaction of the feet with the terrain. So we focused on this second aspect, and we tried to improve the active perception on the foot sole of the ICAB. So we considered a layer of artificial skin under the sole of the robot. So this is the feet, and we had a force-tone torque sensor here. And the challenge here was to use the force torque sensor to actually learn the compliance of the individual sensors locally. So the main idea that we implemented was to consider all the tactile sensors on the skin to be local springs, and to estimate the elastic coefficient for these springs. So this is the model that we get, which is actually pretty simple. And if you are going to come to the interactive section, I'm going to describe in detail. And we both localized the sensors, the skin sensors, with respect to a reference frame, which was common for all of them, and both estimated the compliance coefficients of these sensors. So experiments were performed on two different settings. The first setting where we actually probed the skin normally with respect to the entire surface. And then we tried to generalize the estimation that we got on a different, more natural setting, which was performed while the ICAB was standing on a spherical surface, basically. So yeah, we got some good results in this way, and I'm happy to discuss them later in the interactive section. Thank you.
Good afternoon. So since I'm the last one, Allison said I could have 20 minutes. So this is the work of two of my former postdocs. So Frank Hammond, who will join Georgia Tech as a faculty member, and Yeet Mangush, who's just now joined as a faculty member at Oregon State. So in the past, our lab has innovated in creating entirely soft sensors sensors that are elastomeric in nature and filled with a conductive fluid, in this case a liquid metal. And so we wanted to take these sensors and use them for grasp detection and other haptic interfaces with a human hand. And so we made a soft glove, or we are making a soft glove. So this work is talking about some of the challenges associated with that. In particular, these sensors are typically made using sort of quasi-two-dimensional molds, which makes it tricky to wrap these things around something as complex as a hand, in particular if you have something like 30-something of these sensors. And the second one is the second challenge is related to practical issues in terms of wiring. And so I'll just describe briefly a couple of the innovations described in this paper. The first is embedding wiring directly within these sort of two-dimensional molds. In the past, the way that these sensors work, if you want to sense an extension, then you basically have a more or less a strain gauge pattern in these sensors that such that as you stretch them, the resistance changes and you read them out just as you would a strain gauge. And similarly for a pressure sensor, it's more of a sort of a serpentine pattern, a coil pattern, excuse me, that you add normal pressure to the surface and that collapses the channels and changes the resistivity as well. So the wiring for these was a challenge. We did some simple adjustments by actually having the wires sort of in-molded into the structures while they're being manufactured, which was in the past was an afterthought. The other thing that we tried to do was figure out ways to make sort of modular connections between these physical sensors. You can imagine that if I've got 30-something sensors on a hand and I do it all at once, I have to create a very complicated mold. And so we wanted to just create molds for individual sensors that we then clamped together, and we tested a number of different ways to do that. And then the last thing that we did was once all the sensors are created and wired, then we did a final molding and encapsulation step. Plug these all in. This is a demonstration that we have of 6 sensors, so 3 extension, 3 pressure sensors on a single finger, where you can then put this on your finger and do various different grasp activities, measure pressures and motions, and extract out useful information. There's nothing particularly interesting about this graph other than the fact that you can sort of sense changes in different events, but we're extending this currently to a full glove and various sort of canonical grasping tasks and feedback mechanisms. So I will tell you, I won't, but some of my students will tell you about this at the interactive session if you're interested. Thank you.
That concludes this session. After lunch and after the awards ceremony, please come speak to the authors at the interactive session. Thank you.